Hi everybody, I'm Dr. Kat Vlies from Central New Mexico Community College. We're going to use CNMGlass to learn more about those thick and thin filaments that we find in muscle tissue, and we're focusing on skeletal muscle tissue. Remember, the thick filaments can be called myosin filaments. I'm going to abbreviate filaments, while the thin filaments we can call actin filaments as well. You will also see these filaments being referred to as myofilaments. Remember, myo refers to muscle. Let's take a closer look at what a thick filament looks like. In a thick filament, we find a couple hundred myosin proteins, and they look more or less like this. They will consist of two molecules, each with a tail and then a head, like so, more or less. The head is what's going to bind to the thin filament during a contraction. The head also has a binding site for ATP. Or nearby the head. And then we also find that an Atp Ace enzyme is associated with the myosin molecule. So again, we have about 200 or 300 of these myosin proteins, as illustrated here, inside of a thick filament. And when you look at a sarcomere, please notice that the arrangement of these myosin molecules is interesting. You will not see any of the heads within the H zone. And the reason for that is because there are no thick filaments to bind with there. So why have heads there? So the heads tend to point away from the H zone. Now, what is the role of ATP? We're going to see that ATP must bind to the heads to actually detach the heads from the thin filaments during contraction. But I'm getting a little bit ahead of myself. But still, what is the role of ATP Ace with the binding of ATP, which leads to the breaking of the binding of the heads? Well, remember that ATP can be hydrolyzed into adenosine diphosphate, an inorganic phosphate, and then energy. And for this to be able to happen, we need an enzyme. And that enzyme is called Atp Ace. This is a very important reaction for you to remember for the rest of the semester and for probably many of your future classes in the sciences, ATP hydrolysis. So that's our myosin molecule. Our actin filament is much more complicated. It's made up of 3 different proteins. Now, I'm going to present to you a rather simplified version of a thin filament or actin filament. Your book will show it more realistically. I'm going to keep it simple. For instance, we're going to see, first of all, that the most important or the most common protein found in a thin filament or actin filament is our actin molecules. And it's these actin molecules to which these heads of the thick filaments bind. And so therefore they have a binding site for the heads. Sometimes we call that binding site an active site. So if we jump back for a moment to the thick filament, we refer to these as the heads, or just the head area, and this as the tail area, or just the tail. So all of these little crosses that I'm putting on these actin molecules are the binding sites. Often one of these actin molecules is more specifically called a G-actin molecule, where the G stands for globular, as in round. Okay, now we find that covering these binding sites at times that a muscle is not contracting, we see that these binding sites are covered by a second protein. And that second protein is called tropomyosin. Now be careful. Here we see a molecule that has the term myosin in it, but it belongs to our thin filament, our actin filament. So be careful. And then finally we have a third protein complex. And this is more or less what it looks like. We're going to see that it's made up of 3 components. And how about I first explain the 3 components to you? We're going to have one subunit that we will call TNI, and that binds to actin. There's another subunit that we call TNT. The TN stands for troponin, and the TNT binds to tropomyosin, which is that linear molecule that blocks our binding sites when a muscle cell is relaxed. This is our tropomyosin. Maybe I should also label it here. Our third subunit in our troponin complex we call TNC, and that is because it binds calcium. Calcium ions. Remember, calcium has 2 positive charges. So what does this look like together with our tropomyosin and actin molecules? Well, and again, this is just a sketch. We're going to have one of our subunits bound to our actin. That's our TNI, I'm sorry. Then we're going to have one of our subunits bound to tropomyosin. That's our TNT. And then finally we have a subunit that will bind calcium ions. So maybe what I should do is create little stars like so to illustrate that the TNC has little calcium ions attached to it. This is in a relaxed situation, and also what I have not done is I have not drawn 2 strands of the actin molecules, which are each covered with a tropomyosin strand. So I've kept it more simplified. In real life, you would have a double strand of actin molecules with their binding sites covered with tropomyosin. Okay. Now, what happens when a muscle becomes stimulated by the somatic nervous system is that this electrical current that starts to spread across the cell will stimulate the terminal cisternae of your sarcoplasmic reticulum to let go with a lot of that calcium that they store. So in other words, in the membranes of the terminal cisternae, we see calcium ion channels, and they will be triggered to open in response of the arrival of what is better called the action potential. And just bear with me. You're going to learn what an action potential is all about. Just think of it for now as this wave of electricity that spreads across our muscle cell. And it's that action potential that triggers the opening of calcium ion channels in the membranes of our terminal cisternae. Well, that means that suddenly all of this calcium starts to flood the sarcoplasm where we have our myofibrils made up of our thick and our thin filaments. Remember, your myofibrils are organelles that are bathing in the cytoplasm that are called the sarcoplasm. So all of these calcium ions are dumped into the sarcoplasm, and eventually they are going to start colliding with things, including our troponin complex. And so there will come a point in time when a maximum of 4 calcium ions will bind to our troponin complex. And when that happens, it's going to trigger all of these subunits to start moving. Think of them as 3 soccer balls that start to roll kind of around one another. And consequently, our tropomyosin molecule shifts away. You can think of it being pushed away or pulled away. It doesn't matter. It is this change in the 3-dimensional shape of our troponin complex. Remember, anytime something binds to a protein, it changes shape. So the 3-dimensional shape of troponin changes, and that causes a shift in tropomyosin. When tropomyosin does not bind, or does not cover, I should say, the binding sites of our actin molecules, we now will see that our heads of our thick filaments, so let's say that right here, this represents the head of a thick filament, and here as well, these heads are now going to be able to bind to these binding sites. And that's what's going to allow to move or it allows for the actin filament to be moved into that H zone. And when that happens, when our thin filaments within a sarcomere start to move into the H zone, that shows a form of contraction in the muscle cell. And it could possibly impact the whole muscle organ if enough muscle cells go through this process of what we call cross-bridging. When these heads bind to these binding sites, we call this cross-bridging. And that can ultimately lead to the shortening of the whole muscle cell. So, thick filaments, thin filaments, and a little bit of a discussion on how the heads bind to the thin filaments as a consequence of all of the calcium ions being released from the sarcoplasmic reticulum's terminal cisternae. Thanks for watching. Till next time.